So now we have a notion that lets us talk in a rigorous way about kind of about the relative computational difficulty of problems. So we say P1 is no harder than P2 if there exists this polynomial time reduction from P1 to P2. So you can almost think of the reduction as making the problem harder, right? The direction the arrow points when we're talking about reducing from one problem to another is kind of the direction of increase in hardness, right? So if I've got this P1 and there exists a polynomial reduction to P2, this tells me that P1 is no harder than P2, right? This says P1 is not more difficult than P2. Okay. So here's a question that ends up being a pretty important question, is what are the hardest problems in NP? So we know about this class of NP. What are the hardest problems in NP? And are those problems, and essentially how hard are those problems? So what are the hardest problems in NP? Okay, so if we visualize this class of problems that's called NP, right, the class of problems whose solutions can be verified in polynomial time, what we can do is kind of picture a sequence of problem reductions from easy stuff to increasingly more and more difficult stuff, and ask kind of where does this sequence end? Okay, so we could think of maybe P1 here is the array search, right? The one we've been thinking about for a couple lectures now, and maybe P2 is decision knapsack. Okay. So we know that there is a polynomial time reduction from P1 to P2. We know this because we wrote one in video 3. And you might imagine that there is a polynomial time reduction from P2 to something else, right? So there's more polynomial reductions here, and then you might imagine that this could continue. This could continue on and on and on. So the question is, using this notion of computational hardness that's kind of run by this problem reduction notion, where does this sequence end, right? Or does it? Right. So we can ask, what is the hardest problem in NP? Or you could also say, is there even a hardest problem in NP? Right. So we could also ask, is there a hardest problem in NP? Right, and at the outset, right, without knowing much more about this problem, you might actually think that there isn't. I can always ask a question like, what is the largest number in a set of numbers? And there might not be an answer to that question, right? Just because I'm asking a question that's a well-posed question doesn't mean that there's an answer, right? So asking, is there a hardest problem in NP is you maybe, let me just put parentheses here, maybe this is like asking, what's the largest number? Or is there a largest real number? Right? There isn't a largest real number. That's one of the main facts that you'll learn in analysis if and when you take analysis. And so it's possible that there is no hardest problem in NP. Right? This is a completely, it's not clear that the answer here is going to be something satisfying. So before we settle this, before we say that, yeah, sure enough there is, let's put a definition to this. Okay, so I've drawn this picture and I've said, hey, let's imagine we've got this sequence of problem reductions. Well, suppose for a second that there were a hardest problem in NP. What would that mean? Well, using the language of problem reductions, this would mean that any problem in NP could be reduced to that problem. Right? So suppose there wasn't a question mark here. Suppose there was actually a hardest problem. Well, the fact of being the hardest problem, or a hardest problem, would mean that every other problem in NP would reduce to it, right? Either by a direct reduction, right? Or by being part of this chain that I've already drawn, right? Or something similar. Okay, and maybe there could even be multiple reductions, right? But if there is a hardest problem, what that means is that essentially all of the arrows eventually land there, and there's no arrows leaving this thing that stay in NP, right? That's what it would mean for there to be, a single hardest problem in NP. So let's put some terminology to this, right? So you've heard this term before, but now there's going to be a definition. I'm going to say a problem is NP complete if it is informally the hardest problem or a hardest problem in NP. So a problem is NP complete. Okay? And this is informally, if it is a hardest problem in NP. A hardest problem in NP, right? That's informal. More formally, we say a problem is NP complete if and only if, 1, it is in NP. Okay, so it is an actual member of the class NP, which means that its solutions can be verified fast. And 2, every problem in NP can be reduced to it in polynomial time, right? Every problem in NP is polynomially reducible to it. Okay. So this is just rephrasing. This is just stating in more concrete terms what I was trying to illustrate with this picture up here. Okay, so before we go to kind of the answer to this, before we start to understand what problems are NP complete, it's worth just thinking about what the implications of this could be. So suppose, for example, and let's kind of put ourselves in the shoes of researchers in the 1960s. So in the 1960s, no one knew anything. No one knew anything about NP complete problems. We had this definition, right? You can write this definition down even if there's nothing that satisfies the definition, but we didn't know much about what kinds of problems satisfy the definition. So let's think about possible cases. So 1, there could be no NP complete problems. So 1, there do not exist NP complete problems. Okay, what would this mean? Well, if you had this big class NP, this would mean, anywhere you start, you could create a chain of problem reductions that goes on forever in NP, right? So there could be a sequence of kind of harder and harder and harder problems that never ends, right? You could just keep on going forever, where you have a bunch of reductions that just go on and go on and go on and go on ad infinitum. And I'll just draw a dashed line there to say it continues. And essentially never cycles back on itself, right? There's no reason why that couldn't be the case. No fundamental reason. And there actually are computational classes of problems that have no complete problems. They do not have a completeness property of some kind. So 2, there could be exactly 1, right? There could be 1 NP complete problem. Okay, and so what does this mean? Well, this means that the picture would be something like this. We've got a sequence of reductions that go further and further, and eventually you get to one. Right? You get to a hardest problem where any polynomial time reduction from that problem to another problem takes you outside the class of NP. Right? So there could be an actual single hardest problem in NP. So 3, there could be more than one NP complete problem. Okay, so what would the implication be of that? So there could be more than one NPC problem. Well, what would that mean? So let's just think about it. Suppose there are 2 NP complete problems, So this is just the case where there's exactly 2, right? So here's the class of NP complete problems, and it contains 2. Well, we know for sure that every problem out here can be reduced to every problem in here, right? So that means I could go from this one to either, I could go from this one to either, this one to either. But let's look back at the definition of NP complete. Remember, the definition of NP complete requires that an NP complete problem is in NP, and that every problem in NP is polynomially reducible to it. So suppose this problem is NP complete. That means that it is in NP. So that means if there's another NP complete problem, that this problem has to reduce to it. Likewise, if this one, switch colors, if this one is NP complete, then that means that it's in NP by definition, which means that it is polynomially reducible to any other NP complete problem. Okay? So if there is more than one NP complete problem, then it turns out that every NP complete problem is in some sense equally difficult, right? And we have to be very precise about that sense. We have to be precise about the fact that what we mean when we say equally difficult is that a polynomial time algorithm for one would work as a polynomial time algorithm for the other. It doesn't mean that it would be really, really efficient, right? But it does mean that at least it would still be a polynomial time algorithm. So if there's more than one, then all NP complete problems would be, in some sense, equally difficult. Okay? Or another way of saying this is that if we came up with a polynomial time algorithm for any of those NP complete problems, that algorithm would be a polynomial time algorithm for all. Okay? So, and let me focus in on this because this one's critically important to get. So, or a polynomial time algorithm for one would be a polynomial time algorithm for all. Insert the word algorithm where it needs to be. Algo for all. Okay. And so what that means is that if you wanted to come up with a polynomial time algorithm for NP complete problems, you can just focus on your favorite one of the problems. You know, if there's one that you think is particularly easy to solve, then design an algorithm for it. And if you can get it, then that algorithm automatically, immediately, becomes an algorithm for all the other ones. Because there is an equivalence in some sense between all of these various problems. So what happened in 1971 is that somebody said, one, there exists an NP complete problem. Okay, so 1971, Cook said that there is an NP complete problem. There's a bit of a history lesson here. So there exists an NP complete problem. And this by itself is really important, right? Because what that means is now that's a problem we can focus on. And by the way, this is the SAT problem, the Boolean satisfiability problem. Okay, and we're not going to get into all the detail that we really should in this class, but you know, go look up the SAT problem and familiarize yourself with it, because it's a super important problem. So not too much longer after this, it was discovered that there are actually many NP complete problems. So after this, later, there exist many NP complete problems. And to date, I don't know what the number is, but it's in the large, at least the high triple digits of problems have been defined as NP complete problems. And you know, we've run into a bunch of them, so we've already seen several of these. So some examples include things like the TSP, and so this is in the decision version. Right, our normal TSP that we think about is the optimization version. where you're saying what is the best tour. The decision version says, does there exist a tour with cost no greater than X? So decision version. We've already seen the knapsack. Right, so both of these are the decision versions of them. So a problem called graph coloring in several variants. Coloring, which you can go look it up, but it has to do with, how many colors does it take to color like countries on a map if you don't want neighboring countries to have the same color. So graph coloring ends up being really important and has a lot of implications in things like scheduling. The Hamiltonian circuit problem, which is essentially the TSP problem. So we'll think about Hamiltonian circuits a bit when we talk about approximability and approximation guarantees for the TSP. So Hamiltonian circuit. There's a whole bunch of various kinds of things. I mean, you can run into terms like bin packing and so on and so forth. But for a good reference, take a look at Karp. He published a famous list of 21 NP-complete problems, which is still kind of like the reference list of good problems. But the list of NP-complete problems is long. And the most important thing about them is that if we find a polynomial time algorithm for one, then that becomes a polynomial time algorithm for all.